Right, let's get started. So from now on, let's talk about the derivation of a neural network. So after seeing some application, I mean the back propagation with the vectors, today we're going to see some let's say examples of the derivation of neural networks. For example, first practice was a one-layer neural network with the MSA regression loss. It's something like this. We have input layer, X was input, and output layer, Y was output, and we have a one single layer, one single hidden layer with parameter W and B. B was bias. Our goal, I mean the training on neural network means finding the optimum parameter W star and P star. So how can you find this? As we discussed in previous slide. So first we have defined loss gradient with respect to W and loss gradient with respect to the P, and update your loss gradient by using gradient descent algorithm. That's going to our strategy. So the question is how to find out this one. Loss gradient with respect to W, loss gradient with respect to P. So in this scenario, we have three layers. For example, linear projection layer here. Z is equal to W times X plus P. And then, because this is a neural network, we have active function. In this case, sigmoid function. So the actual function defined like P equal to G of Z. Z was output of linear projection, and G of Z is equal to 1 over 1 plus exponential minus G. Then finally, we need loss function, which was the MSE regression loss. MSE regression mean y is the ground truth data and P is equal to output after exponential function. So it should be connected to like this. X and Y are training sample. X and Y and equal was a training sample. So in this case, let's make a vector form of the input and output or intermediate feature vector. For example, X was the d-dimensional vector. Let's say d-dimensional vector or d times 1 vector. W. In this case, W should be matrix. The size of W should be M times D. So for the shape commutation or simplicity, let's suppose that W consists of the M rows, where each row vector, let's say W1 in T space. So it means that W matrix should be like W11, W12, W1D, W21, WM1, WMD. So it should be M by D matrix. Of course, we also have a bias, which is the M by 1 vector. 써봅시다. M by 1 vector. So it means that W times X plus B equal to G, right? Of course, Y is M by 1 vector, which means we just assume that we have an M class, M kinds of class label. Sorry, indeed not M class label. It should be the like regression problem. So yeah, YM is just our target, right? So this is our setting. First of all, as we discussed in previous lecture note, let's consider graph form. I mean the I'll say, okay, let's go back to here. So first of all, set the computation graph. 그렇죠? computation graph. So in our case, in this setting, can be represented like this. First of all, X is here. WT is a linear transform or 뭐라고 했죠? linear projection. 그렇죠? linear projection layer and sigmoid layer after MSA loss layer, right? And input should be d by 1 vector, and z, which was the output of the linear projection layer, should be m by 1 vector. After sigmoid function p should be m by 1 vector. Of course, y was m by 1 vector. So it means that we will have loss value. So this is our computation graph. So in this setting, let's talk about the backpropagation. 자, first of all, we have x, which was input data, right? In forward propagation, let's say forward propagation, we should compute each node value or just value, let's say from x to g to the p to the l. Because we already have current w and p, and sigmoid doesn't have any, I'll say, trainer parameter. MSC does not have a trainer parameter, so just compute the z to p to the l from x. This is for propagation step, right? And in backpropagation step, we can just start from the loss layer, right? So let's see here. In loss layer, we just focus here, not considered any, I'll say, previous layer. So this is just a function. This function, right? This function takes the y and p as an input and l as an output. It means that, first of all, let's compute the loss gradient with respect to the output. So it should be L to the L. It's going to be L. So this is the upstream gradient, right? So in this function, downstream gradient should be L loss gradient with respect to P. Let's say vector P. So in this case, there is the, it just directly computed because there's no loss gradient, the local gradient term, right? So it's going to be L to the P. Right after that, L to the P, it's going to be the new upstream gradient, right? And we are interested in downstream gradient for the backpropagation, right? So to do this, we require what? P over G, which was the local gradient, right? Then, right? Then what happened? Our downstream gradient can be just like a local gradient times upstream gradient, right? So this is just the backpropagation. So after that, this one is going to be the new upstream gradient, right? So for this function, we have a 3 input x, w, p. So it means that there's that z, right? It means that for the backpropagation, we have to know local gradient z over x, z over w, then z over p, which is going to be local gradient, right? Then by using this, we finally compute downstream gradient L over x, 다음에 L over w, then L over p. Then this one can be used in gradient descent algorithm to update and to find the optimal W star and B star. That's going to be our backpropagation. It's very simple, right? It's very simple. The question is the only remaining question is how to find the local gradient for the sigmoid function and local gradient for the linear projection layer. That's going to be our objective. So from now, let's talk about how to find out local gradient for the segment function and local gradient for the linear projection layer. That's it. Alright, so let's do that. Now, first of all, let's talk about the linear projection layer. So we have to consider the analytic gradient to compute the say, local gradient for the linear projection layer. Here, the linear projection layer. Right. So as we discussed here, our vector setting. Z was the vector. Let's say m dimensional vector. So it means that it consists of the m kinds of element. And W was the matrix, each consisting of the m row vector. Right? And X was just like t dimensional vector. Of course, P is equal to P is just like m dimensional vector, right? Right. So in this case, first of all, each row, this is just a linear system. So it means that each row represents each equation, right? Each equation. So first of all, Z1 is equal to W1 transpose X plus B, right? Let's say P1, 그렇죠? Z1 should be this row vector times this column vector plus P1. This. It can be written again like W11, X1, W12, X2, blah 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 plus P1. Like this. Right. So, based on definition of the gradient, here, so vector to scalar or vector to vector, please remember this one. We can easily derive local gradient. For example, Z1 over, for example, vector W1. The scalar vector to scalar going to be just the vector x itself. Right? You can just do that. So which mean it's in D space, D by 1 space. You can just do that. You can. I will skip the detail, but you can just derive something like this. For example, because Z1 is just like scalar value, so it's going to be Z1 over W1, Z1 over W2, Z1 over, let's say W. Sorry, don't 1, 1, 2, W1, T, 맞죠? 1T. So it's going to be the just vector P, vector X. So it's going to be the just vector. Similarly, local gradient with respect to let's say P1, for example, it's just like 1. Similarly, Z2 over W1, vector W1 is equal to 0. Because when we just consider W2, I have Z2, there was no related term. There's no W1 related term. It should be 0. And Z2 over P1 also should be 0. Similar. So based on such observation, not just observation, based on such a computation, Z1 over W1 is equal to X. Z2 over W1 is equal to 0. Zm over W1 is equal to 0. Thus, gradient of Z over gradient of Z in terms of the W1 should be T by M vector, T by M matrix where Z was in our M space and W1 is in our T space. It should be T by 1 vector, T by M matrix. So from here, it's going to be the vector X and it should be the zero vector, blah, blah, blah. So this is just a Z over W1. Similarly, based on such a rule, similarly, Z over Wi should be 0, 0, 0, 0, X, 0, 0, 0, which is in T by M matrix, where this X is located in J's index. In this case, the first index, the W2 is, when W2 case, it should be the second index, blah, blah, blah. And similarly, Z over B, it's equal to just the identity matrix based on such observation. So it's in M by M space, right? So this is the local gradient for linear Poisson layer. Local gradient for the linear Poisson layer. It's very easy, right? Right. So from now on, let's move to the local gradient for the sigmoid function. Where sigmoid function defines as like g of z, which is equal to 1 over 1 plus exponential negative g. Right, so please remember that this is this one, z was the vector. It means that g, z was also vector, right? Right. Okay, z was in m by 1 space. It means that gz also in m by 1 space. So it means that sigmoid function is element independently defined. Right. So let's derive this one. So first of all, people derive the vector form for the scalar case. If the z was scalar, gradient of the gz in terms of g can be represented by this. So it's very simple. Just compute the gradient in terms of the g. Then we can rewrite this one as well, like this and this times this. So it's going to be 1 minus gz times gz for the scalar case. Similarly, we are interested in the vector form. 그렇죠? Z was in our m by 1 space. Let's talk about gz over z. Because this is the vector to vector case, we can just compute local gradient of z1, scalar z1 over z1 and z2 z1 z2 gz2 here and g2. So for the scalar case, we derive here, but in this case, it's not a z2 and just z1. So in this case, sigmoid function was defined independently for each element. It should be 0 and it should be 0 because there is no z1 relevant term in the z2, gz2. It should be 0. So similarly, this one is going to be the diagonal of the 1 minus gzi times gzi. It's going to be 1 minus gzi times gzi, blah blah, 1 minus gzm, which is in m by m space, m by m matrix space. This is just the local gradient. Local gradient. So for sigmoid function. That's it. Right, so it's done. Now we have a local gradient and loss function, then just backpropagate from the loss layer to the input layer. Right, let's do that. 자, first of all, because the loss L, MSA regression loss L was like y minus p. Right? So first of all, loss gradient with respect to p. Let's go back to here. P with respect to p should be just a 2 p minus y from here. Just a p minus y. After that, loss gradient with respect to g should be loss gradient with respect to p and local gradient p over g. 이렇게 like this. By chain rule here. We derive the gradient, local gradient for the sigmoid function, which should be like this. So from here, it should be like this. So it's going to be the L over G, right? Similarly, 써볼까요? It's going to be upstream gradient. It's going to be local gradient. It's going to be downstream gradient. 그렇죠? Right. So after that, loss gradient with P, it's going to be upstream gradient. Upstream gradient and local gradient. Right. So G over P here was identity matrix. It's just identity matrix. So it's going to be the L over G itself. Similarly, when try to say L over W. But here is a problem. W, in our case, W was the M by T matrix. So it's not just vector. So far we just discussed vector to vector case or vector to scalar case. But W is a matrix, right? So to do this, where W was like the W consisting of W1 transpose, W1 vector, W2 vector, Wm vector as a row vector, right? So based on this observation, we decompose loss gradient with respect to M as a loss gradient with respect to W1, loss gradient with respect to W2, and loss gradient Wm, where Wm is just like D by 1 vector, right? Each W vector was D by 1 vector, right? So it's going to be the scalar 2 vector case, right? Right, so here, loss gradient with respect to W1 can be easily computed by G over W1 times loss gradient with respect to G1. G. 3. Okay. G over W1 times loss gradient of G, which was from here. It's going to be the upstream gradient. It's going to be the local gradient. Then it's going to be downstream gradient. Right. So we have to know this one. Z gradient with respect to W1. Right. Here. 맞죠? This vector. This matrix. So by multiplying upstream gradient to the local gradient, it's going to be the X times loss gradient with respect to Z is the first Z is the first element. Right. It means that L over Z it's like the m by 1 vector, which means it consisting of the L over Z first element, second element, blah blah. So it's going to be the first element times x. Similarly, this one is going to be the first element of the L over G times x, and this one transpose. By rewritten this term as a simple form, it's going to be the L over G times x transpose. Finally, we found L over W and L over P, which means it can be used in gradient descent algorithm. Descent algorithm to find out optimal double star and B star. That's it. So this is the one layer neural network with MST regression loss case. Very simple. 자, let's summarize this one in Korean again. 자, 아주 빠르게 설명할게요. 뭐 너무 간단한 얘기였는데 이렇게 이제 원래 neural network 아주 심플한 케이스도 생각해 보면 이렇게 세 가지 레이어로 구성되어 있어요. 리니어 프로젝션 레이어, 액티비티 펑션 레이어, 로스 레이어. 그래서 이 팩터 이렇게 구성되어 있는데 이거를 이제 어떻게 하냐면 우리가 얘기했던 그레디언 백프로파게이션 풀려고 하면은 이제 이런 계속 백프로파게이션 건데 이렇게 펑션들, 그러니까 로컬 그러니까 업스윙 그레디언, 다운스윙 그레디언, 업스윙 그레디언트를 정할 수 있는 펑션들로 바꾼 다음에 백프로파게이션 쭉 한다고 했죠. 그래서 여기서는 지금 세 가지 펑션, 리니어 프로젝션 펑션, 피그모이드 펑션, MST 로스 펑션을 나왔어요. 그래서 쭉쭉쭉 백프로젝션 하면 되는데 문제가 그런 로컬 그레디언트를 알아야 된다. 그래서 이 리니어 프로젝션 쪽과 피그모이드 펑션들의 로컬 그레디언트를 애널리틱하게 찾아놓는 거예요. 이렇게. 그렇죠? 이걸 가지고 위에서부터 쭉 백프로파게이션 한 거죠. 그래서 우리가 이제는 W와 P를 옵티마이즈 할 거면 WP를 로스 그레디언트 알아야 했으니 이걸 가지고 이제 그레디언트 사이즈까지 넣어버리면 우리가 W 스타와 B 스타를 찾을 수 있다 라는 거예요. 따라올 수 있죠. Then I'd like to give you a quiz, short quiz. It's not a one layer from now, it's going to be a two layer with MST regression law. The shape of the neural network should be like this. And this is a function, right? So this is going to be our short quiz homework. So you can just check this homework at our Blackboard website. Please submit this one before our next lecture. Okay. 아마 여러분들이 여기까지 이해했다면 이것도 아주 쉽게 풀 수 있어요. It's going to be very, very easy if you just understand what I've done so far. So please try to that. Right, so this is the regression case with the neural network. Right? So from now on, let's move to the classification case. Classification case. So from now on, you have a same vector x and output layer y, and of course you have a reliable parameter w and p. I mean the one layer. So of course our objective is going to find w star and p star, right? And similar to the previous example, our input was a t by 1 vector, w consisting of the m kinds of row vector, w1, w2, and wm, which is going to be the m by t matrix, and bias p was the m by 1 vector. But in this case, we are interested in the classification case. So our y n. I mean the our y. It's going to be just the class index. For example, this x input categorized as a second class. It should be 1 here. Remaining should be 0. So it's going to binary class index. Let's say 써볼까? Binary class index, for example. Of course, it should be in, let's say, C by 1 space. It means that we have a C kind of class. In this setting, we also have a 3-layer linear operation layer, z was equal to w times x plus b, active function layer in this case, not just a sigmoid function, active function, 그쵸? which was the softmax, 그쵸? softmax, and loss layer. In softmax classifier, loss was like the log likelihood loss, or error loss. In this case, first of all, let's represent your neural network as a set. The set of the sequence of the functions. For example, linear operation layer. Linear operation layer. And softmax layer and error loss layer. Of course, output should be L. So similarly, this is a classical problem, but it's going to be almost the same as in MSC case. So first of all, in forward propagation case, just compute Z and P and L from the X, which values will be used in backpropagation. Alright, this is the forward propagation. And then in backpropagation, we sequentially compute the loss gradient. For example, loss gradient with respect to P, right? So, and loss gradient with respect to the G, and loss gradient with respect to X, and loss gradient with respect to the W, loss gradient with respect to P. Of course, similar to the previous example, we have to know the local gradient. 그렇죠? For each function, right? So the question is how to define local gradient for the linear operation layer, softmax layer, and error loss layer analytically. That's going to be our question. So from now, let's talk about how to find the local gradient. Alright. So first of all, because we already defined the local gradient for the linear operation layer, let's talk about the local gradient for the softmax function, which was defined that P was equal to exponential G over sigma G, where sigma G was the sum of the exponential ZG. This is the definition of the softmax function, right? It's just like this. Z and sigma, softmax function, the output should be P vector, right? Where Z was n by 1 vector, probability, the output of the softmax was n by 1 vector as well, right? In this case, we are interested in P over G. So first of all, P is the n by 1 vector, and G was n by 1 vector. Then, what is the size of the P over G? Gradient of P with respect to the G. It's going to be n by m. Right? Then, this matrix can be written as like P1 over G1, P1 over G2, P2 over G1, P2 over G2, blah blah, and PM over GM, like this, right? Like this. But we just faced some problem because this one, when we enlarge this one, P1 can be just represented by exponential G1 over sum of exponential G1 plus exponential G2 blah 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 exponential of Gm, like this. And similarly, when we just consider this one, it's going to be the G2, right? So it's relatively complicated comparing to the sigmoid function case because due to this denominator term. But still we can do that. We can do that. So please try to derive yourself. Then after deriving some mathematical tool, when we just define this matrix as of D, and when we just define this value as a D11, this one as a D21, this one is a D12, and this one is a D22, blah blah blah. And TAB element can be represented like PA times delta AB minus PB, where delta AB was equal to 1 if AB is equal to A and B, A equals to B, I mean the diagonal term, and delta AB is equal to 0 otherwise. Then PA and PB, it's going to be just like your set. Just like this one, 그렇죠? element vector is. So by this observation, your final local gradient can be represented like this. 그렇죠? So please derive this one yourself. Due to time limitation, I will just skip this one. Anyway, this is going to be the gradient. Local gradient for subtext function. Right. Similarly, comparing to the MSE loss, now when we are interested in the local likelihood loss, which is relatively complicated. But because in MSE loss function, it was just like the, y minus p length was a derivation of the y minus p was just 2 L minus y. 아이고. to here, 그렇죠? But compared to MSE regression loss, log likelihood loss is relatively complicated. So let's talk about this one. LW, log likelihood loss was like minus log PYN, where P is the probability after softmax and Y is class label. So it means that local gradient with respect to the L, because L is the output itself, it's going to be the n by 1 vector. It means that where loss value with respect to the variable P1 써볼까? loss with respect to P1 was equal to 0, and loss gradient with respect to the PM was 0 as well, and loss gradient with the PYN only have some value because the loss just the function of the PYN, so it's going to be just like minus 1 over PYN because this is log function. So it's going to be minus 0, 0, 0, 1 over PYN 0, 0, 0, 0, where YN's index. Right. That's it. Right. So now we have a all of local gradient. Right. So from now on, let's backpropagate. 자, first of all, let's go back to this one. 그렇죠? From loss layer to the softness layer to the linear pressure layer. 자, and to the loss gradient with the P was like this one. 그렇죠? From here, right? And L over G is going to be the P over G local gradient times offset gradient L over P. It's going to be like this. Up, local, down. By multiplying this one and local gradient for the softmax function here, we can achieve this one. It's going to be the P minus 1. It's very interesting. I'll just skip the detail, but please try to derive yourself. But after this one, we just achieve P minus 1. This is the theory of the softmax with error loss, as we discussed in previous slide. So by backpropagating, this just be the P minus 1, right? P minus 1. What's that? P minus 1. When you just consider softmax plus loss function as just one function, it should be exactly same. That's very interesting observation. Anyway, similar to the linear regression case, L over W and L over B can be found by backpropagation. This is going to be the training phase. That's why we have to know the backpropagation. The only difference was here. So, and remaining thing is going to be exactly the same in linear regression case. Even though you have a one or two more layers, you can do similar things. That's a theory of the backpropagation, right? So you have one more case, two layers on that with the subtomatic classifier. It should be like that. So it's going to be the second homework. You can just check this homework at our Blackboard website. So please check and please submit this homework before our class. Okay? Right, so this is just the derivation of neural networks. So that's it. So from now on, let's talk about the optimization. So we'll just discuss the gradient descent algorithm. Loss, when we have a loss function, we want to minimize and we want to optimize W in terms of W. L of W in terms of W. So from now on, in deep learning era, we want to introduce one more terminology, FPOC. One FPOC means path through all training data. For example, let's suppose that you have a training sample where number of training data is M. In this case, let's say this is M because this is a different notation. Anyway, one FPOC means path through all training data. So it means that MMPOC means MF mean pass through the all training data and compute the loss gradient and update the W and repeat M time. This is just going to be the gradient descent algorithm. Why? Because the L, in this case L, loss gradient just related to hold the vector. 그렇죠? Hold the say training set. So this is going to be the L gradient offset rule, gradient descent update rule. But we just face the problem. For some, it's going to be very, very expensive when M is very, very large. For example, if we consider something like n kinds of sample, it should be the loss gradient should be the sum of the n kinds of one. But in deep learning era, n is equal to very, very huge value. For example, like n is equal to 1,000 or 2,000. It's going to be very, very huge. In this case, it's really hard to compute the local gradient as just some value. So, in deep learning era, we use mini batch concept. We approximate the sum using the mini batch of the examples 32, 64, or 128. The concept is very, very simple. It's like this. Let's suppose that you have n kinds of training data, m kinds of training data. In gradient descent algorithm, the original gradient descent algorithm itself, we just consider these n kinds of samples, training samples, at the same time and compute the local gradient. But it's going to be very, very challenge. So in mini batch case, just grouping the training data as a mini batch, just a set of the sample, the subset of the sample as a 32 or 64 or 208, 128, blah blah blah. Then compute the local loss gradient for each batch independently. That's going to be our new strategy. From now, we will call this one is a stochastic gradient descent, or mini batch gradient descent, or just SGD. This is just a advanced version for updating your neural network, not just with gradient descent algorithm, but the philosophy is exactly the same. So from now on, we are interested in M epoch, but for each epoch, from now we just consider the each training batches consisting of the P kinds of sample. For example, like 32 or 64, blah blah blah. From now we'll say this is a batch. This is a number of batch. Another probability, number of sample in the batch. Then update each parameter for each training batch. Of course, we repeat m times. So, for example, let's say that your training sample is at 124, and you are interested in the update your parameter 500 times. Then in original gradient descent, your W just updated 500 times, right? But in gradient descent algorithm, when you consider the 32 number of sample in the batch, the number of bits is going to be the 1 over 24 over 32. It's going to be 32 again. Then, because there's 2 for loop, your update rule can be repeated by 32 times m. m is equal to 500, so it's going to be the 500 times 32. It means that you update parameter 32 times better, more compared to the original gradient algorithm. So this is going to be the stochastic gradient descent. Advantage is more accurate estimate of gradient, and image leads to the fast training, can penalize computation, significantly speed increase on each GPU. So like this. So this is just the loss landscape, and this one represents gradient descent algorithm. So because it considers the whole training sample at the same time for each sample, it's going to be more accurate, but it's going to be very slow. But in stochastic gradient descent, we very fastly compute each gradient, but in some case it may be noise, but after iterating the some iteration, we finally converge it to the better minimum, faster than original gradient descent algorithm. So that's going to be the stochastic gradient algorithm. So it is called the SGD. So from now on in deep learning era, we will talk about this. We will use this SGD. Of course, there are so many kinds of advanced optimizer, the momentum, blah blah blah. So we will talk about this one later. But if you are interested in, please check this slide. Okay, so that's it. So this is the end of the image classification and neural network part. We have 2 homework in this lecture note. Please check this one and submit before the deadline. Right, so that's it. Here. So we finished the neural network, and we have a first one to implement the one very simple neural network. So before that, for this homework project, you have to know the Python tutorial, Python. But I will just skip this part. I already did this Python tutorial already. So this is very simple, and I just assume you already have some knowledge in Python. So if you are just a beginner, please just follow this tutorial. So it just takes less than 2 hours. So anyway, please check this one. Here's the homework. Project 1. So in project 1, we will implement neural network. Right, so in our project 1, we will implement 2-layer neural network with a software classifier. So this was our short quiz, 그쵸? 2-layer neural network with a software classifier. In this project, we will use a CyPark-10 image classification dataset, as we discussed here. 그쵸? So we have a 2 weight, W1 and W2, and bias, B1 and B2. And our prediction output is going to be like this: W2 times value, W1 times X plus B1 plus B2. To notice that in our previous example, nonlinear function was the sigmoid, but in this case just value. So please remember that. And our loss should be data loss. So transfer slow like loss plus L2 regularizar to W1 and W2, not B1 and B2. The IPython notebook 2-layer net.ipython will work with you through the implementation 2-layer neural network classifier. So it's not just from the scratch, but we just gave you skeleton code. Just work with this IPython. which currently suggest you using the Anaconda Python distributed, which provide an easy way for you handling the package dependencies. What I'm going to do is make sure that create the virtual environment. Yeah. So this is the explanation about the Anaconda virtual environment setting and install. 그죠? Installing the package and downloading the dataset and do the following. Fill the code following the instruction in Markdown cell, two-layer neural network Python and classifier / neural network part. There are start of your code and end of your code tag, denoting start and end of code section. You should fill up. Then you will finally get the loss graph and loss history and visualization of your learned network. Okay, so this is your first homework. It's going to be very, very fun. Right, so due date, it's going to be March 29, Sunday. I mean the after our meeting exam. Before the midnight. There it's going to be a latent policy. You must submit the code with a report, one page with a free format, including a description of your code, result and discussion. Report should be written in English. Finally, please do not copy your friend's one or internet sources. I and TA have all kinds of sources for this project. So we can just check. We can just check your copy. So please try to do yourself. And please start your project as early as you can. Okay. Right. So that's it. So this is about project 1. Okay. So if you have a question, please let me know or TAs know. And so we will move to lecture note, convolution neural network. Maybe this is going to be the next topics. Right. Thank you very much. No more question. It's not question. Anyway, thank you very much and see you next time. 자, 여러분 방금 진행했죠? 그래서 이제 프로젝트 1 나갔어요. 그래서 아마 쭉 읽어보면 되고 우리가 거기 올려줬어요. 프로젝트 1 탭에다 올려줬으니까 쭉 확인해서 결국에 여기만 하면 돼요. 여기를 잘하면 되니까 여러분 한번 뉴럴 네트워크를 처음 써보는 친구들 또는 해본 친구들이든 요 뉴럴 네트워크를 한번 스크래치부터 짜보는 걸 해보면 많은 도움이 될 거예요. 알겠죠? 그래서 해보면 좋겠고요. 우린 다음 시간부터 렉처 6으로 넘어갑시다. 수고하셨습니다.